Welcome to this video on load flow analysis. In this video, we shall continue with our learning outcome number 2, that is load flow solution. In the previous video, we have developed the load flow equation. Now in this video, we shall look at the techniques of load flow solution. So this is the load flow equation that we have already developed in our previous video. Now, what is the before going to the solution of this equation, let us understand the characteristic of this equation. This equation is non-linear algebraic equation. Now, which are the terms present in this equation that makes it non-linear? So, the power, the real power and reactive power terms present in this equation make this equation non-linear, because all of we know that power is proportional, whether it is real power or reactive power, both are proportional to I square or V square, and that's why this equation is non-linear. And as we know that there is no direct method of obtaining solution to nonlinear equations, we have to rely on numerical techniques. So there are many numerical techniques available in the literature, but we shall learn this load flow equation, power flow equation. We will use this numerical technique. The first is Gauss-Seidel method. The second one is Newton-Raphson, then decoupled and fast decoupled. Now here decoupled and fast decoupled, these are not a new methods, but they are extension of Newton-Raphson method. So we see it later on. What is how these are the extension of Newton-Raphson method. But these are the techniques, numerical techniques we shall use for the solution of load flow equation. Now let us see how load flow is performed by Gauss-Seidel numerical technique. Now in the Gauss-Seidel method, the importance is given to voltage at the buses, and hence the voltage equation is obtained from the power flow equation. So the power flow equation is reformed, or we can say it is converted into the voltage equation. So how it is done? So this is the power flow equation already we have developed in video 4th, and in this equation now this summation, from this summation one term, that is YII term, VI term is taken outside. So when this term is taken outside, so this one term we can see it is taken outside, and rest of the terms they are still kept in the summation form. So it is written here k is not equal to I, because this term is taken out from this summation. Now from this equation we are getting the equation for this VI. We are trying to get this equation. So we can see here VI equal to 1 divided by YI in bracket Pi minus JQI divided by VI conjugate minus summation YIKBK. Now this is the equation which we have to remember. This is the voltage equation that is solved in the Gauss-Seidel method for obtaining the load flow solution. So this is the voltage equation which you will have to remember, that is solved iteratively. What is iteratively? We will come to know in the next slide. Once the voltages are known, then the line flow, bus power and losses, they are determined. Okay, so here the point is to be remembered that in the Gauss-Seidel method, the importance is given to the voltage at the buses, and they are determined. The voltage of the buses, they are determined by this equation. That is what we have derived here. And after obtaining the voltages, then the line current, the line flows, power flow, burst power, losses, all the load flow parameters, they are then determined. Okay. Now, let us understand with an example how the equations or voltage equations are obtained in the Gauss-Seidel method and how they are solved with an example. I'm not going to solve the example, but just I'm giving an idea so as to understand what is voltage, how voltage equations are obtained and how they are solved. Now, in this three-bus power system, we can see the first bus is slack bus. They are mentioned. It is mentioned that the first bus is slack bus, and when it is slack bus, already we know that in the slack bus, voltage is specified. So, voltage magnitude is specified 1.05 and its angle is also specified. Now, then what we have to determine? We have to determine what is the real power and what is the reactive power that is to be given by the generator so as to meet the load and the losses in the transmission system. Okay. Now, the second bus here, it is told that uh, then now here we have given a real power, that is P is specified, that actually this is a load bus. When it is a load bus, then we know that P and Q are specified. Now P is specified, it is 256.6 megawatt, and Q is also specified. That is, what is the reactive power requirement of the load? It is 110.02 MVAR. Now P and Q are specified. Here we have to find out what is the voltage magnitude. That is, what is V2, voltage at this bus, and what is its corresponding angle. These two parameters we have to take. Then come to the third bus. At the third bus again, they have, it is a load bus. At this load bus, P is specified as 138.6 megawatt and Q is also specified, that is 45.2 MVAR. Then we have to find out what is the voltage, that is V3 voltage at this bus and what is its corresponding angle. So now you hear, now this is what is our problem. Now at first bus, at bus number 1, we have to determine P1 and Q1, that is what is the real power and reactive power. These two parameters we have to determine. Voltage is known. At second bus, we have to calculate the voltage V2 and delta 2. At third bus, you have to calculate the voltage, sorry, this is V3 and delta 3. Now, in the Gauss-Seidel method, as I already told, that importance given is given to voltages, or first the voltages are determined. Okay, now what we have to do, we have to, V1 is already known, so there is nothing to worry about the voltage at this bus. We have to calculate what is V2. First, we have to calculate what is voltage at V2 because that is not known. Then at the third bus again, we have to calculate what is voltage V3. So first importance is given to voltage in Gauss-Seidel method. Now what is voltage equation? Already in the previous equation we have derived the equation for voltage VI equal to 1 divided by YII in bracket PI minus JQI divided by VI conjugate minus summation k equal to 1 and k is not equal to I up to n yik into vk. This is the voltage equation that already we have derived it in the previous slide for the power flow equation. Now I will convert this is in general, that is for ith bus, but now I will convert it to V2. So what I will do in this equation, I will substitute I is equal to 2. That is, I want voltage at second bus. That is one thing. Second thing, here we are interested, we want what is n here. N is the number of bus in the system. Now in the present system, we have n is equal to 3. So what we will get the equation, how this equation gets modified. Now I substitute I is equal to 2. So V2 is equal to 1 divided by Y22 in bracket P2 minus JQ2 divided by V2 conjugate minus summation k equal to 1, k is not equal to 2 and 3. Now my number of buses in the system is 2, y2k and vk. The equation gets modified to this. So I can write the equation now for v2. V2 is equal to 1 by y22 P2 minus JQ2 divided by V2 conjugate minus, now I will expand this summation as y21 V1 plus y22 will not come, y22 will not come because k we should not take equal to 2. So the next term it will be y23 V3. So this is the equation what we get for V2, that is for voltage at the second bus. Now we have to solve this. Once we solve this, then we get the value of voltage V2. But there is one problem, there is one glitch here, that V2 term is also on this side. So it is not explicit equation, it is an implicit equation. Because of this reason, and there is also a non-linearity because of this power, the present of these terms, then we have to use numerical techniques to solve this equation. Similarly, now V3 also we require a V3. Now similarly we can develop the equation Y33 P3 minus JQ3 divided by V3 conjugate minus Y31 V plus Y32 V2. Now these two equations, equation number 1 for V2 and equation number 2 for V3 voltage. Okay, as I told previously that we are interested in voltage. In Gauss-Seidel method, we are interested in voltage at the buses. V1 is known. So now we want voltage, V2 voltage and V3, and these are the two equations. Now these two equations we have to solve it iteratively or using numerical technique. You have to remember that all the numerical techniques, they are iterative methods. They are iterative method. What is the concept of iterative method? Is that first we make the assumption. We make the assumption. And based on assumption, for example, here now I want V2 and V3 voltage. Now for both of these two terms, you make an assumption. Now say that V2 is 1 at an angle 0, V3 is 1 at an angle 0. These are not the correct answer, these are the assumptions. Now based on these assumptions, you calculate the correct value. Find more accurate value. You can say more accurate, not exact accurate, more accurate value. Now then, after finding this voltage, now you get the value of V2, that we say that it is after the first iteration, and V3 value, that is after the first iteration. Now you make a check. Now you have to check whether the value what we have calculated, they are correct or not. And we can use different convergence criteria here. We will discuss it later on. And if the check is okay, if the value what we have calculated, they are the accurate values or the final values, then we can stop, or else we have to repeat this calculation. You have to repeat this calculation. Again, you go back over here and again find more accurate value, that is second iterative value, and again check. And if the convergence criteria, or if the calculated values, if they are found correct, then stop, or else go to next iteration. So this repetitive calculation of voltages, what we call it as iterations. Okay, so this is what I want to tell, that important point is that in the Gauss-Seidel, importance is given to voltages. Voltage equations are obtained, and those equations, they are solved iteratively. Okay. Now, uh, let us understand this Gauss-Seidel method, or understand what is exactly mean by iteration with an simple example. So I'm not using now, I'm not doing any, doing not load flow. Instead, I'm taking one general example. Suppose if I have an equation, say it is 2x square equal to 4x. Now, in this equation, you can see this is non-linear because x square term is there. Okay, and maybe even though it is not, but there may be a direct method of solution to this, or but I will solve this equation by Gauss-Seidel method. Okay, so now what is my variable here? The variable is x. I want the value of x for which this equation gets satisfied, or LHS become equal to LHS. Now, if you look at this equation, we can directly say that if x is equal to 2, suppose this is my, uh, actually, if you look at this equation and if you use your logic or some understanding, we can say for x is equal to 2, LHS become equal to RHS. Suppose if you substitute 2 here, then we get 2 LHS, I write here LHS equal to RHS. So if you substitute x is equal to 2 here, then it becomes 8 and equal to 8. So LHS become equal to RHS, then x is equal to 2 is your solution. Now this x is equal to 2 we have obtained just by our understanding or by our logic. Now I will show this x is equal to 2 on a number line. Suppose this is x number line, and here this is our x is equal to 2. This is the answer for this equation, or the solution to this equation. Now in numerical technique, in Gauss-Seidel, how we get this x is equal to 2 answer? So what we do here in the Gauss-Seidel, how it is done by numerical technique? So what step 1, guess is made, what assumptions is made, assumption. In the previous slide also I told that we have to first make assumption for our variable. Now our variable is x here. In the load flow in the previous problem we have seen we have two variables v2 and v3, and we have made an assumption. Now in this problem x is the variable, and we make now the assumption x is equal to, say I make an assumption, say 0.5. This is not the correct answer. The correct answer is 2. But I make an assumption. So say that here we have x is equal to 0.5. This is not the correct answer. The correct answer is x is equal to 2. Now from this assumption, we have to go to this correct answer stepwise. So what I do in the next step, now I want more correct value. So how I can find step 2? So get the more correct value. I say that more correct value, not more correct value. So what I will do, I will write the equation as x is 2x square is there, 2x square is equal to 4x. So this 2 you take it on this denominator, so it becomes 2x, and x is equal to square root of 2 into square root of x. So this is what the equation you get now. Now what you do, you get the first correct value x of 1, that is your first calculation. So root 2 into, now in the x I will substitute 0.5. So root of 0.5, and you will get this value as, I think, 1. Let me check it. Yeah, we get an answer as 1. But now we have obtained x is equal to 1. Here we have obtained x is equal to 1. But this is not the correct answer. This is more accurate value, which is closer to 2. This is not correct value. Now what we go? Now we go for the second iteration, x of 2. Once again we calculate the value of x. Now again root 2 into root x. Now in the x we substitute the more correct value. So we get here it as root 2. But root 2 is also not an correct value. So we go x is equal to root 2, that is 1.4142. This is not also correct value. Okay, now you go for the third iteration. X of 3 is equal to root 2 into root x. Now in place of x, you substitute root 2. You substitute root 2. So root 2 into root 2, you will get it as 2. Now you reach to the correct value. Now once you get the correct value, then you stop the iteration. Stop. Or else you may go to next iteration. So in all the numerical techniques, this is what this philosophy is adopted. First, first we make an assumption, and based on assumption we calculate the more correct value. Then there is made and check based on the convergence criteria, whether the solution whatever we have obtained, is it the final value or it is the correct value. If it is not, then we go for repeat for calculating for again repeated calculation. So these calculation or iterations, they are continue till we get the final value. Okay, so in this video what we have learned, just I will what important note we have to take from this video is that uh, okay, so here we have to obtain that in this we have to first understand what is the characteristic of the power flow equation. The power flow equation is non-linear, and we have to rely on numerical techniques. And these are the techniques which are available to us: Gauss-Seidel, Newton-Raphson, decoupled, fast decoupled. And now uh, in the Gauss-Seidel method, the power flow equation is converted to voltage equation. In the Gauss-Seidel, voltage importance is given to voltage, and the voltage equations, they are solved iteratively. Okay, and that we have seen with this example, load flow, how load flow is performed by using Gauss-Seidel, how voltages are calculated iteratively, and we have understood what is Gauss-Seidel with a general example. So in this video, up to this only, we shall continue in the next video with the flow chart of Gauss-Seidel method. Okay, thank you very much.